So for this next example, we have to start being a little bit careful about the sign of the different quantities. So remember that velocity and acceleration are vector quantities. Now, if you're talking about direction in a straight line, so it can really only travel in two directions, and that's why in this case we can start using positive and negative. Otherwise, if we hadn't specified that it was in a straight line, your velocity would have to have like a proper vector direction. It would have to have some angle associated with it. But in this case, where we've only got traveling along a line, then we can only have travel in two directions. And usually when you've got a situation like that, you'll just deal with that using positives and negatives. And so in this case, we've got a robot and starts 5 meters from a point A. So we're defining a position. We could call this X. We might even call it X. We could call it displacement. And the usual symbol for displacement is an S. But let's just call this X. And so then we're going to have, what else do we have? So it wants to know after 4 minutes, what's the displacement of the robot from A and what total distance has the robot traveled? So the idea of this example is just to highlight what the difference is between displacement in this context and distance traveled. And so it can often be nice to draw a bit of a sketch. And so we've got some kind of robot who knows what it looks like, a couple of wheels like so. And so what you can do is you can just show on, I've shown the position it's starting from, and we can have a think about, we can actually show its velocity as well. So it's going like so, and it's heading in this direction, and it's going 50 millimeters per second in the negative direction. Okay, so I'm not putting the negative in here because I've shown the direction with the arrow. That's what this negative means. So what's the displacement after 4 minutes? What's the displacement from A? So let's figure that out. So first we'll just write down the usual equation. So the displacement, that's an S for displacement usually. I don't know why, but it is. And then it's the starting displacement plus the the velocity. We're talking about constant velocity here. And the velocity is a constant. So usually if it's a constant, you'll just show it as V naught, for example, times the time t. Okay, so distance is velocity times time is basically what that's saying, but you're allowing for the fact that it might not be starting at zero displacement. So here we're starting at a displacement from A of positive 5 meters. Okay, it could be negative 5 meters, could be over here, but it's starting from positive 5 meters. So in this case, we've got 5 plus, so V naught is minus 50 millimeters per second, so it's heading in that direction, times time, which is 4 minutes. And so we need to change that to seconds. So we've got consistent units. So it's 4 minutes, 60 seconds in a minute. So it's 4 times 60. And then we can just calculate that now. We've got another problem here. This is millimeters per second. And the starting position is given in meters. So that's also not going to work. So what we should probably do first is we'll just drag this down. I might even, it's okay. And so what I'll do first is just write down the quantities we know and convert them all to consistent units first. So S naught equals 5 meters, which is equal to, so there's 1,000 millimeters in a meter, so it's 5,000 millimeters. And we also know that V naught, that's cool, is equal to 50 millimeters per second. And that's where I'm going to keep those units. I'm going to change everything else to be consistent with those units. And we know that T is equal to 4 minutes, which equals 4 times 60 seconds. You could do 60 seconds over 1 minute. Do you know what I mean? You can do the fraction thing. I've kind of shown you how to do that, and now I'm ignoring it. So let's just do it. So you've got 4 minutes times, and there's 60 seconds in every minute. Those will cancel out. And so therefore you're going to get 240 seconds. Okay, and so it could be nicer just to figure out all that stuff with consistent units first. So then we'll just change this straight to 240. So let's correct all this stuff now. So we're going to have S naught is equal to 5,000 plus. Now I just need to be careful with this. it wasn't 50 millimeters per second, it was negative 50 millimeters per second, so it's heading in the negative direction. So we're going to get S naught is 5,000 plus negative 50 millimeters per second times 240 seconds, which is equal to 5,000, it's going to be a 1,200, I think, isn't it? Let's just check that. Hold on, just need to find my calculator. So it's going to be 5,000 minus 50 times 240 is equal to 12,000, 12,000 millimeters. So therefore, the answer is going to be 5,000 minus 12,000. So that's going to be 7,000 millimeters negative, which is equal to negative 7 meters. And does that make sense? So let's have a think about this. So it's going 50 millimeters every second. And what it's actually going to end up with, so this is going to be at, at time equals 0. And then let's just draw where it's going to end up. So it's going to head all the way through here, and it's going to end up at minus 7. 1, 2, 3, 4, 5, 6, 7. Scale's not great, but anyway. So this is at time equals 4 minutes. It's going to be here, the little robot, and it's still going to be heading 50 millimeters per second in that direction. Okay, and so it's come all the way past A and come all the way to here. And so what the displacement from A will have to go past here first. And so it's gone past A and gone to the other side. So the displacement from A is now minus 7 meters. What's the total distance that that robot has traveled? So let's just write that out actually first. Displacement. So the displacement from A is equal to minus 7 meters. And the total distance traveled so distance is not a vector, and we're not interested in the position relative to A, displacement from A. So displacement from A is basically the position relative to A. That's what it's talking about. But the total distance traveled is just going to be that 12 meters. Okay, so you're just looking at relative to where it started, how far has it gone? So it's just going to be 12 meters. Okay, and that's our two answers for this question. So it's just showing you the difference between this quantity displacement and that depends on where it's relative to. You know, the displacement from the starting point would have been minus 12 meters. Okay, it's gone 12 meters in this direction. So it would be minus 12 meters. So displacement, you have to think about what direction is positive, what direction is negative. So displacement from the starting point would have been minus 12 meters. But the displacement from A, from this position we're choosing as A for our 0 for displacement, then it's only minus 7 meters. Because it started positive 5 meters. And the distance traveled is just what you'd usually think about. It's just velocity times distance, or speed times distance, really. And it doesn't have a direction. So total distance traveled is just 12 meters. That's the total length of the path that that little robot has followed. Was that everything for that question? So this would be A. B, well, I've already got A. It should be up here somewhere. Yeah, put it there anyway. Okay, so let's have a look at the next example now. We'll get to multiple stages in a minute. That's another time where you have to think about the difference between distance traveled and displacement as if it's multiple stages. And I think we've got one in a minute that'll look at that.